The latest symbolism caught by the James Webb Space Telescope has left specialists in awe, uncovering the universe in ways that were once thought to be beyond our understanding. These images are not only enhancing our comprehension of the universe but also revealing perplexing phenomena that suggest our current knowledge may not be sufficient to fully grasp the early development of the universe. Settled theories about the universe's origins are now facing challenges, pushing the scientific community to explore alternative theories regarding its inception. This raises a crucial question. How did the universe come into existence, and why are these pivotal discoveries presenting difficulties even for the most seasoned experts in astronomy? This necessitates a more thorough examination of the true nature of the Big Bang and its evolving complexities. It may be time to reconsider the theory of cosmic origins itself, especially since its portrayal has often been oversimplified by the public. The Big Bang was not merely an explosion occurring within pre-existing space, it marked the very birth of space itself, unfolding around 13.8 billion years ago, alongside matter and time. A central concept in modern cosmology is that of a singularity, a point where gravity becomes so extreme that the fabric of spacetime becomes infinite. Following billions of years since the universe's inception, it has become evident that our cosmic home is part of a much larger system. For scientists, this discovery has provided a fundamental insight into the universe's ongoing expansion, suggesting that space itself continues to evolve, contrary to past theories that suggested otherwise. It is believed that the first stars began illuminating the universe around 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age, when the first bright celestial bodies formed and started evolving into galaxies. However, the speed at which these galaxies developed remains a mystery. A remarkable moment occurred on July 22 when the James Webb Space Telescope unveiled its first set of images, showcasing several galaxies, some of which had already existed around 300 million years after the universe's creation. These galaxies, though younger than those observed today, were smaller and less massive, aligning with the scientific models of the time. In the early universe, the matter density was believed to be too low to form galaxies as massive as those we observe now. This discovery began with the detection of 6 distinct, red-shifted bright spots, illuminating one of the greatest cosmic puzzles in recent history. These newly identified galaxies, despite their youth, appeared nearly as large as our own Milky Way, sparking curiosity among researchers in the field of Big Bang cosmology. When scientists analyzed a set of images taken by the telescope's near-infrared camera, they confirmed the presence of these distant galaxies. They used redshift data to determine that the light from these galaxies had traveled for over 1 billion years before reaching Earth. This suggested that these galaxies had formed between 570 and 700 million years after the Big Bang. This astonishing finding challenges conventional cosmological expectations, which predicted much smaller, less developed galaxies at this stage in the universe's timeline. Instead, the James Webb Telescope revealed galaxies nearly as massive as the Milky Way, contradicting these predictions. The stars within these galaxies had already accumulated masses exceeding 10 billion times that of the Sun, with one galaxy possibly surpassing even this threshold. However, whether this hypothesis is entirely accurate is still under discussion. Even if these findings prove correct, the mass of the early universe would have been far greater than previously expected. To complicate matters further, the discovery of these galaxies presents a serious challenge to nearly all traditional cosmological theories. Even if just one of these galaxies is confirmed to be accurate, it would necessitate a reassessment of our assumptions about the early structures of the universe. The matter density in the early universe would have to be significantly higher than initially believed. Another possible explanation is that these galaxies may have formed through mechanisms that are entirely unknown to us. These discoveries have raised questions that require a reassessment of the Big Bang theory. Many astrophysicists have expressed frustration with these findings, frequently voicing their concerns in scientific journals. Those who question standard theories are often labeled as unconventional or extreme. However, it is clear that even those who support the Big Bang theory are facing troubling inconsistencies. Among these is the fundamental question: how could something have emerged from nothing 13.8 billion years ago? Did something truly arise from nothing, or was there an external catalyst for this event? Did the Big Bang occur randomly? Stephen Hawking famously pointed out that the very concept of time itself began with a Big Bang, meaning the event could not have been initiated by something else or triggered externally. Similar uncertainties surround the uniformity of radiation and matter across the universe. No matter where we look, or at what distance, we observe a similar distribution of galaxies, nebulae, and radiation. Modern scientists often explain this uniformity with the theory of cosmic inflation. However, some researchers have expanded upon this idea, proposing that the universe expanded in a more chaotic manner. According to this hypothesis, expansion occurred only in isolated regions, like bubbles, while other regions continue to expand indefinitely. This model raises the fascinating possibility that multiple universes could exist within these expanding bubbles, each governed by its own unique set of physical laws. Such a perspective suggests that our universe may not represent the entirety of existence, but could instead be part of a much larger and more complex structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe is proposed. This is just one of many cosmological theories. For instance, a 1955 article in NASA's Hotshot magazine suggested that the universe may never have experienced a Big Bang and could have always existed, possibly for an infinite period. In this interpretation, the universe's expansion would be non-existent, and the continuous formation of matter would create the illusion of gradual growth over time. One particularly captivating theory emerging from quantum physics and string theory suggests that our universe might be a projection or simulation originating from a higher dimensional reality. While this might sound like the plot of a science fiction story, it connects to the concept of the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization, capable of utilizing the energy of a galaxy, might theoretically be able to create a perfect simulation of a universe. However, proving the validity of such a scenario remains an enormous challenge. Exploring the depths of cosmology and the origins of the universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new imagery from the James Webb Space Telescope has reignited debates about the fundamental fabric of existence, driving scientists to test established theories and rethink core concepts regarding the cosmos. At the heart of this discussion lies the theory of the universe's origin, which serves as the foundation of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from a hot, dense state, rapidly expanding and giving rise to the space-time and matter we observe today. This grand event wasn't merely an explosion within pre-existing space, but also marked the creation of space itself. The concept of a singularity, where gravitational forces become so intense that space-time curvature becomes infinite, underpins our understanding of the early universe. However, the discovery of massive, mature galaxies just a few hundred million years after the Big Bang challenges conventional ideas about how quickly early cosmic structures could have formed. These findings imply that the early universe had a far higher matter density than previously believed, raising significant questions about how such massive structures could have emerged so rapidly. This forces cosmologists to reconsider how galaxies, like those observed by the James Webb Space Telescope, could have formed so early in the universe's history. One key theory affected by these revelations is cosmic inflation. Cosmic inflation, a widely accepted theory, suggests that the universe underwent a rapid exponential expansion in the moments immediately following the Big Bang. This expansion is thought to have smoothed out irregularities, explaining why the universe appears so uniform on a large scale. However, the discovery of massive galaxies so early in cosmic history raises questions about whether this model fully accounts for the observed distribution of matter. If these early galaxies were indeed as large and massive as the Milky Way, their existence challenges our understanding of how structures formed in the early universe. Current models predict that galaxies should have taken far longer to accumulate such mass, given the expected rate of matter collapse and star formation. The James Webb Space Telescope's findings suggest that either galaxies formed much more efficiently than we thought, or our theories about dark matter, gravity, and cosmic evolution need revision. Another intriguing possibility is that the fundamental laws of physics may have operated differently in the early universe. Some researchers speculate that gravitational forces could have been stronger, or that unknown processes facilitated the rapid growth of these ancient galaxies. If confirmed, such deviations from standard physics could revolutionize our understanding of the cosmos and require a rethinking of fundamental concepts like dark matter and dark energy. These discoveries also raise philosophical and existential questions about the nature of reality itself. If our current models struggle to explain the earliest stages of the universe, could it be that we are missing a deeper, more fundamental theory of existence? Some physicists propose that our universe might be just one of many in a vast multiverse, where different physical laws and constants govern each cosmic region. String theory and quantum mechanics have introduced the idea of higher dimensions, suggesting that our observable universe might be a mere projection of a more complex, multi-dimensional reality. If true, this could imply that what we perceive as the Big Bang was merely a localized event within a much grander cosmic framework. Furthermore, the notion that the universe might be a simulated construct, an idea once relegated to science fiction, is gaining traction among some theoretical physicists. If an advanced civilization could harness immense computational power, it could theoretically simulate entire universes, complete with self-aware beings like ourselves. While speculative, such hypotheses push the boundaries of our understanding and force us to reconsider what we accept as reality. The James Webb Space Telescope's revelations have reinvigorated debates about these profound questions. Scientists now face the challenge of reconciling these unexpected findings with established cosmological models. New theories, revised calculations, and even entirely novel frameworks may be needed to explain how the early universe evolved so rapidly. Regardless of the ultimate conclusions, one thing is certain: our quest to understand the universe is far from over. With each new discovery, we are reminded of the vast, uncharted mysteries that lie beyond our current comprehension. The cosmos continues to surprise us, challenging our assumptions and pushing the boundaries of human knowledge. In the coming years, further observations from the James Webb Space Telescope, as well as future space missions, may provide additional clues that help unravel these cosmic puzzles. Until then, the universe remains an open book, filled with mysteries waiting to be decoded by the next generation of scientists and explorers. Which suggests that the universe expanded dramatically following the huge explosion. This quick expansion is thought to explain the consistency of the cosmic microwave background radiation we observe across the universe today. However, the latest discoveries are introducing complications that may require adjustments to our understanding of expansion. The formation of these massive early galaxies also raises fundamental questions about dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework for galaxies to form, scientists still lack a clear understanding of its distribution and properties in the early universe. Due to these unresolved mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang theory. Some of these models suggest that our universe could be one of many within a vast multiverse, each governed by its own physical laws and constants. These ideas, which stem from string theory and quantum cosmology, propose a far more intricate and interconnected universe than previously imagined. One increasingly popular theory is the concept of eternal inflation, where universes continually emerge within a larger, ever-expanding space. This suggests that our universe may be just one bubble among many, each with its own distinct physical properties. The challenge, however, lies in finding observational evidence to support these speculative ideas, as they push the boundaries of what can be scientifically tested. Another provocative hypothesis posits that our universe may be a computer-generated simulation, drawing parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems. If this theory were true, it would drastically alter our understanding of reality and spark significant philosophical and scientific debates about the nature of existence itself. As observational astronomy continues to advance, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to uncover even more of the universe's secrets. Future observations may provide further insights into the earliest moments of the universe, potentially revealing clues about its ultimate fate and the fundamental principles governing its ongoing evolution. Meanwhile, particle physicists remain dedicated to uncovering the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal in theoretical physics. In the realm of quantum mechanics, debates over the nature of time continue, with some theories suggesting that time itself may be evolving or even changing at the most fundamental levels. Understanding the concept of time in the context of cosmology could revolutionize our perception of the universe's origins and its continuous development. Furthermore, the search for extraterrestrial life continues to captivate both public interest and scientific research. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could reveal biosignatures indicating the presence of life beyond our planet. As scientific exploration progresses, so too does the philosophical inquiry into humanity's place in the cosmos. The search for answers to questions about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will continue to shape discussions in both scientific and philosophical circles. As we push the boundaries of scientific discovery, we find ourselves at the crossroads of new revelations and long-established theories being challenged. The growing body of data from instruments like the James Webb Space Telescope is revealing a universe far more complex than we had ever imagined. Each new discovery forces us to confront the limitations of our current understanding and pushes us to reconsider fundamental concepts, from the origins of the universe to the very nature of existence itself. The James Webb Space Telescope's images have sparked widespread discussions, particularly regarding how galaxies formed in the early universe. The question of how galaxies could form so quickly after the Big Bang is now one of the most pressing issues facing cosmologists. According to current models, the early universe should have been far less capable of producing large, mature galaxies so soon after its inception. However, these new findings suggest that the formation of massive galaxies may have occurred at a much faster rate than previously believed. One of the critical issues raised by these discoveries is the concept of cosmic inflation, a theory central to our understanding of the early universe. According to this theory, the universe underwent an extremely rapid expansion immediately after the Big Bang. This expansion is thought to have explained the uniformity of the universe and the smooth distribution of matter. However, the discovery of large, developed galaxies at such an early stage challenges the idea that the universe expanded uniformly across all regions. This discrepancy suggests that the early universe may have been far more complex than current models can account for. As scientists continue to analyze the data from the James Webb Space Telescope, they are re-evaluating the role of dark matter and dark energy in the formation of these early galaxies. Dark matter, which is believed to provide the gravitational scaffolding for galaxies, has long remained elusive. Its exact properties and distribution in the early universe are still unknown. These new findings could provide crucial insights into some of these unanswered questions. Similarly, dark energy, thought to drive the accelerated expansion of the universe, is another component that scientists are now beginning to explore more deeply in light of these discoveries. The implications of these findings extend beyond our understanding of galaxy formation, challenging the very structure of our cosmological models and urging us to ask deeper questions about the universe itself. How did the universe evolve from the chaotic and dense state of the Big Bang to the structured systems we observe today? What role did dark matter and dark energy play in this transformation? And most importantly, what do these discoveries tell us about the future of the universe? The expanding frontiers of cosmology. As our understanding of the universe deepens, scientists are grappling with increasingly complex questions that challenge long-standing theories. The latest observations suggest that the early universe may have been far more dynamic than previously thought, forcing researchers to reconsider key aspects of cosmology. One of the most significant challenges arises from the apparent inconsistencies in galaxy formation timelines. If massive galaxies existed shortly after the Big Bang, the standard models of cosmology may require revision. The role of dark matter in this process remains a major mystery. While it is thought to provide the gravitational scaffolding for galaxies to form, its nature and behavior in the early universe remain largely unknown. The ongoing search for direct evidence of dark matter continues through experiments on Earth and observations in space. Similarly, dark energy, the force thought to be driving the universe's accelerated expansion, poses fundamental questions. If dark energy's influence was different in the early universe, it could reshape our understanding of cosmic evolution. Some alternative theories suggest that dark energy may not be a constant force but rather a dynamic component that changes over time. If this is the case, it could have profound implications for the ultimate fate of the universe. Revisiting the nature of reality. Beyond cosmology, new discoveries are reigniting debates about the fundamental nature of reality itself. The hypothesis that the universe may be part of a multiverse suggests that our cosmos is not unique but one of many, each with distinct physical laws. This idea, which emerges from theories like string theory and quantum mechanics, raises profound philosophical and scientific questions about existence. Another radical idea gaining attention is the simulation hypothesis, the notion that our universe might be an artificial construct, a vast digital simulation created by an advanced civilization. This concept, while speculative, is being explored through advancements in quantum physics, information theory, and artificial intelligence. If the universe does operate on some underlying computational framework, it would redefine the way we perceive reality, consciousness, and the laws of physics themselves. The search for life beyond Earth. While physicists explore the deepest mysteries of the cosmos, another frontier of discovery lies in the search for extraterrestrial life. The rapid discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our knowledge of planetary diversity. Scientists now estimate that billions of potentially habitable planets may exist in the Milky Way alone. Future missions, including studies using the James Webb Space Telescope, aim to analyze the atmospheres of exoplanets for biosignatures, chemical markers that may indicate the presence of life. The detection of molecules such as oxygen, methane, and water vapor in an exoplanet's atmosphere could provide the first evidence of life beyond Earth. Beyond exoplanets, scientists are also investigating the potential for life within our own solar system. Moons such as Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are believed to harbor subsurface oceans beneath their icy crusts. These environments, heated by gravitational interactions, may provide conditions suitable for microbial life. Future robotic missions, including planned probes to these moons, may offer groundbreaking insights into the possibility of life beyond Earth. The future of space exploration. As scientific knowledge advances, so too does humanity's ambition to explore space. Governments and private companies are investing in missions that could one day lead to human settlement beyond Earth. NASA's Artemis program aims to return humans to the Moon, with plans for a permanent lunar base that could serve as a stepping stone for future Mars missions. Meanwhile, SpaceX and other private companies are developing technologies that could enable long-term human presence on Mars. If successful, these efforts could mark the beginning of a new era in human civilization, one in which humanity expands beyond Earth and becomes an interplanetary species. However, space colonization presents immense challenges, including radiation exposure, psychological effects of long-duration space travel, and the need for sustainable life support systems. Overcoming these hurdles will require groundbreaking advances in engineering, biology, and space medicine. A universe of unanswered questions. Despite the extraordinary progress made in cosmology and space exploration, many questions remain unanswered. What existed before the Big Bang? Is the universe infinite, or does it have an edge? What is the true nature of dark matter and dark energy? And perhaps the most profound question of all, are we alone in the universe? As technology advances and our observational capabilities improve, scientists are optimistic that answers to these questions may emerge in the coming decades. The discoveries made so far have already reshaped our understanding of the cosmos, and the next generation of telescopes, space probes, and particle physics experiments promises to deepen our knowledge even further. Conclusion: the dawn of a new era in science. Humanity stands at the precipice of a new scientific revolution. Every new discovery pushes the boundaries of what we know and forces us to reconsider long-held assumptions. Whether through advancements in astrophysics, quantum mechanics, or the search for extraterrestrial life, the coming years will likely bring breakthroughs that challenge and redefine our understanding of the universe. As we continue this journey of exploration and discovery, one thing remains certain: the cosmos holds secrets far beyond our current comprehension. The pursuit of knowledge, driven by curiosity, technology, and the unrelenting quest for truth, ensures that the mysteries of the universe will continue to inspire and captivate generations to come.